Hello, everyone. Welcome. Hi, I'm Oliver.
Hi, I'm Lily.
Science and Easy English with Oliver and Lily.
Can we actually reverse aging?
Yeah, so what if I told you that right now in a lab at Harvard, scientists aren't just like slowing down the biological clock, they are actually flipping a switch to turn old blind mice back into healthy young ones with fully restored vision.
Which is just wild to think about.
It really is. So today, we're doing a deep dive into a really fascinating stack of research papers, clinical trial reviews, and biotech industry news, all of it centered on the biology of aging. And our mission today is to figure out, how close we actually are to doing that to ourselves.
Right, and just to set the context right out of the gate here, we are not talking about, like, anti-aging skin creams or cosmetic quick fixes.
No dubious wellness trends today.
Exactly. We are looking at the literal resetting of the biological clock at a fundamental cellular level. Like, the science has really moved from cosmetics into the realm of deep biological intervention.
Which honestly sounds a bit like science fiction. But before we can even talk about reversing aging, we have to define what aging actually is on a biological level. Because, for most of human history, we've just looked at the calendar, right? Chronological age.
Yeah, the strict number of years you've been alive.
Right. But the research makes this very clear distinction between chronological age and biological age. And biological age is it's the actual measurable wear and tear on your cellular machinery.
And that distinction is basically the foundation of this entire field. To categorize that wear and tear, scientists rely on what they call the hallmarks of aging.
Which used to be, what, 9 hallmarks?
Yeah, originally 9, then 12, and now the scientific consensus recognizes 14 interconnected processes that literally cause our bodies to age.
Okay, but I want to get away from just like reading textbook lists and actually look at the mechanics of a few of these. Take telomere attrition, which is probably one of the most famous ones.
Oh, definitely.
A lot of people use the shoelace cap analogy for this, where the plastic tips wear down. But the papers we looked at frame it a bit differently. It's more like a physical book that gets endlessly photocopied.
I actually love that analogy.
Right. So telomeres are essentially these blank buffer pages at the beginning and end of your DNA sequence. Every time a cell divides and, copies its DNA, the copying machine basically misses the very last page.
Because those pages are blank, losing them doesn't hurt the actual important genetic instructions. But eventually, after like 50 or 60 divisions, you run out of blank buffer pages.
And then it starts tearing into the actual text.
Exactly. It hits the critical genes. And this mechanism creates a hard ceiling for human cellular division, which scientists call the Hayflick limit. It basically mathematically caps the maximum human lifespan at about 120 years.
Okay, let's unpack this. What happens when a cell actually hits that limit? Does it just quietly die and get flushed out of the system?
You would really hope so, but no. And that brings us to another major hallmark, which is cellular senescence.
The zombie cells.
Yes, the zombie cells. When a cell accumulates too much DNA damage, or its telomeres get too short, it triggers this DNA damage response. It sort of knows that if it divides again, it might become a cancerous tumor.
Yeah.
So it pulls the emergency brake, it locks itself down.
So it refuses to divide.
Right, but it also refuses to die.
Wait, if they are damaged and completely useless, why doesn't our immune system just clear them out like it normally does with a virus or a dead cell?
Well, when we're young, our immune system does exactly that. But as we age, that immune clearance slows way down, and these zombie cells start to accumulate in our tissues.
Ah, that doesn't sound great.
It gets worse. They aren't just sitting there passively. They actively secrete this toxic cocktail of inflammatory proteins called cytokines.
Right, the papers described it like a panicked factory worker.
Yes. Imagine a worker who hits the emergency stop button, but then grabs a megaphone and starts screaming, causing all the healthy workers around them to panic and stop working too. They drive local chronic inflammation that aggressively ages all the healthy tissue around them.
Wow. That paints a pretty vivid picture. But, looking through the stack of research, there was a newer hallmark that really caught me off guard. Because we usually think of aging as purely physical, right? Like diet, exercise, toxins.
Mm-hmm.
But the research now recognizes psychosocial isolation and mental illness as a physical driver of aging.
Yeah, the concept of the social geroexposome. It's a massive shift in how we understand human biology. The data clearly shows that severe social stress, poverty, and chronic loneliness, they don't just affect your mood, they physically accelerate cellular aging.
But how does a feeling like loneliness actually turn into a physical aging process in a cell?
It all comes down to evolutionary biology, really.
Yeah.
Specifically the NFKB signaling pathway. Think about our Paleolithic past. If you were isolated from your tribe, you were in imminent physical danger.
Like from predators or infection.
Exactly. So the brain interprets loneliness as an acute physical threat. It signals the body to preload its immune defenses. It ramps up pro-inflammatory pathways to prepare for a wound that, well, never actually comes.
Oh, wow. So in the modern world, being chronically lonely just leaves your body in this permanent state of low-grade inflammation.
Which rapidly accelerates the creation of those zombie cells we just talked about.
Yeah,
Your social environment is literally writing instructions to your biology.
that is wild. But okay, if all 14 of these hallmarks, from shortening telomeres to chronic inflammation, if they're all interconnected, it makes me wonder what the ultimate root cause is. Like, what starts the cascade?
And that leads us straight into the information theory of aging, or ITOA, which was pioneered by researchers like David Sinclair.
Right.
But to grasp this, you really have to understand the profound difference between the genome and the epigenome.
The genome being your DNA, right? It's digital, highly stable, the hard-coded blueprint of who you are.
Exactly. But every single cell in your body has the exact same DNA. So why does a brain cell look and act so differently than a skin cell?
That would be the epigenome.
Yes, the epigenome is a system of chemical tags like DNA methylation that sit on top of the genome and turn specific genes on or off.
I saw a great analogy for this in the notes. Like, if your DNA is the sheet music for a symphony, the epigenome is the conductor.
Oh, that's a perfect way to put it.
Yeah, the sheet music doesn't change, but the conductor tells the violins when to play loudly and tells the brass section to stay quiet. But unlike the DNA, the epigenome is analog, meaning it is highly susceptible to environmental noise, stress, and damage.
Precisely. And the information theory of aging proposes that getting older isn't driven by accumulating permanent mutations in our DNA hard drive.
It's not.
No. Aging is the progressive loss of youthful epigenetic information. Because of all that analog noise, the inflammation, the stress, the cell divisions, the conductor basically loses their place in the sheet music.
So the violins start playing when they shouldn't? The cell forgets its identity, like a kidney cell forgets how to function like a healthy kidney cell.
Exactly. But the theory also proposes something called the observer concept.
Which honestly sounds a bit like magic at first glance.
It really does. But it's grounded in serious molecular biology. The observer concept suggests that a backup copy of your youthful epigenetic instructions, like the original way the conductor was supposed to lead the symphony, is secretly stored in every single cell, even when you are 90 years old.
Wait, really? So the blueprint of your youth isn't destroyed?
No, it's just inaccessible.
Okay, here's where it gets really interesting. Researchers are actually accessing this hidden backup in the lab using something called epigenetic reprogramming. They are using this specific set of genes called Yamanaka factors. Can you break down how that actually works without getting too lost in the jargon?
I'll try. So Shinya Yamanaka won a Nobel Prize for discovering that if you expose an adult cell to 4 specific transcription proteins, often abbreviated as OSKM, you can wipe its epigenetic slate completely clean. You turn it back into an embryonic stem cell.
Wow.
But what longevity researchers are doing now is using a partial dose, just the OSK genes, without the M.
Okay, why without the M?
Because they express these genes in an older animal just long enough to reset those chemical tags back to their youthful patterns, but not so long that the cell forgets what organ it belongs to.
Right. And that's exactly how they restored vision in those older mice from the Harvard study. They reprogrammed the cells and the optic nerve, basically resetting the conductor, and the mice literally regained their sight.
And they even took mice that were genetically engineered to age prematurely and extended their lifespan by roughly 40%.
40%?
Yeah. What's fascinating here is it's a fundamental shift in how we view biology entirely. For decades, the dogma was that aging was a one-way street of permanent hardware damage, just a slow, irreversible decay, like rust on an old car.
But this theory proves that aging is actually a software glitch.
Exactly. It's an information retrieval problem. And theoretically, that software can be rebooted.
That is just a profound paradigm shift. But, it raises an immediate practical question. If we have the theory to reset the biological clock, how do scientists actually verify that the software is rebooting? And, what treatments are people currently experimenting with outside of those highly controlled mouse labs?
Well, to measure the process, scientists rely on epigenetic clocks. These are these complex algorithms that read those specific patterns of DNA methylation, the chemical tags we talked about, to estimate your biological age.
Okay. And as for treatments,
One of the most rigorously studied drugs in the longevity space right now is rapamycin.
right, I see rapamycin everywhere in these sources. But wait, isn't it an FDA-approved immunosuppressant, used for organ transplant patients? Why are longevity researchers so obsessed with it?
Because in animal models, it consistently extends lifespan by 20 to 25%.
That's huge. How does it do that?
Rapamycin works by inhibiting a specific protein pathway in the body called mTOR. And mTOR is essentially a nutrient sensor. Like when you eat a big meal, mTOR signals your cells to grow and divide. But when you inhibit mTOR with rapamycin, you basically trick your cells into thinking they are starving.
And why is tricking your cells into thinking they're starving a good thing?
Because it triggers a biological process called autophagy. Autophagy is basically your cells conducting a deep microscopic recycling program. They stop trying to divide and instead focus on cleaning up internal garbage, misfolded proteins, and damaged parts.
So it's a cellular Marie Kondo routine, just throwing out what doesn't spark joy.
Exactly.
Huh.
But I will say, the data on humans taking rapamycin is vastly more complicated than the mouse data.
Yeah, the sources highlight the recent PEARL trial, which stands for Participatory Evaluation of Aging with Rapamycin for Longevity. It was this highly anticipated, placebo-controlled human trial, but the results were quite nuanced.
Very nuanced.
It didn't melt away visceral belly fat, which I know a lot of people were really hoping for.
No, it didn't. It did show some compelling improvements in lean muscle mass and pain reduction, particularly for women at higher doses. But the broader takeaway was just that human biology is stubbornly complex.
Now, there's also a piece of modeling data from that trial, right, where they ran the blood work through an epigenetic clock algorithm called PhenoAge, and it estimated that the rapamycin group saw a 4-year reduction in biological age.
They did, yes. But we need to approach that with strict scientific caution. That 4-year reduction was based on group averages and mathematical modeling.
Right.
In fact, they had to estimate several missing data points just to run the algorithm. So it is a tantalizing signal, absolutely, but it is not literal, individualized clinical proof that their bodies became 4 years younger.
Right, so we can't get ahead of ourselves.
Yeah.
But there is also a completely different approach detailed in a recent Stanford study involving something called gerazymes, specifically a protein called 15-PGDH. What exactly is a gerazyme?
So a gerazyme is an enzyme whose levels naturally increase as we age, and its primary function seems to be actively driving tissue degradation.
Okay.
The Stanford researchers found that 15-PGDH breaks down prostaglandins, which are molecules our bodies desperately need for muscle and cartilage repair. As we get older, we produce way too much of this gerazyme, so we lose the ability to repair our joints.
And the breakthrough was that when they chemically blocked this specific enzyme in old mice, they actually regenerated joint cartilage, and they restored muscle strength. The tissue essentially healed like it belonged to a young animal.
Which is a remarkable leap forward, especially for something as notoriously difficult to treat as osteoarthritis. By simply removing one master roadblock, the body's latent regenerative pathways naturally kick back into gear.
Okay, but I have to ask the obvious question here. If rapamycin extends mouse lifespans by 25% and blocking gerazymes regenerates mouse cartilage so beautifully, Why are these therapies available at my local pharmacy today? Like, why is the leap from mice to humans so incredibly difficult?
It really comes down to what longevity researchers call the dimmer switch dilemma. Remember, rapamycin is fundamentally an immunosuppressant.
Right.
You want to turn the dimmer switch up just enough to trigger autophagy and cellular cleanup. But if you turn the switch a fraction too high, you suppress the immune system to the point where a healthy, older adult could contract a severe, potentially fatal infection.
Oh, wow.
Finding that precise, universally safe dose for humans who have wildly different genetics and environments than lab mice is a monumental clinical hurdle.
Yeah, I can imagine. But, that clinical hurdle certainly hasn't stopped the flood of capital. The longevity industry is experiencing a massive biotech boom right now. I mean, the anti-aging market hit $85 billion in 2025 and is projected to reach $120 billion by 2030.
The private sector is moving aggressively. You have companies like Altos Labs, which launched with billions in funding, focusing entirely on cellular resilience and reprogramming.
Yep.
Then there is Life Biosciences, aiming to bring actual epigenetic reprogramming therapies to human clinical trials within the next few years.
The one that really caught my eye was Retrobiosciences. They are taking a very modern approach by using large language models, like the same underlying AI architecture as ChatGPT. And I mean, I use an LLM to help draft emails, so how exactly does an AI chatbot help reprogram a cell?
It's an ingenious application of the technology, actually. Proteins are essentially biological language. They are long sequences of amino acids.
Okay.
Just like an LLM can learn the grammar of English to predict the next word in a sentence, and AI can learn the grammar of biology to predict the physical shape and function of a protein sequence. Retrobioscience is using AI to map out complex cellular networks and design new synthetic molecules that might act as safer, more precise Yamanaka factors.
That is genuinely wild to think about. AI design in biological software. But with all this futuristic promise, the sources also included a really necessary reality check from Dr. Matt Kaberlein. He's a leading longevity researcher, and he laid out 4 specific myths about where the science currently stands. And I think it's crucial we walk through them so you, listening at home, can separate the genuine science from the marketing hype.
Definitely. His first point addresses exactly what we discussed earlier. We cannot directly measure biological age yet.
Right, the clocks.
Yeah, those epigenetic clocks are brilliant analytical tools, but they are statistical estimates correlated with aging. They're not absolute definitive speedometers of your biological decay.
Okay, myth number 2 is something anyone who listens to health podcasts needs to hear. Supplements are not the magic bullet. Dr. Kaberlein emphasizes that basic lifestyle interventions like diet, prioritizing sleep, and regular exercise are fundamentally more powerful than any supplement on the market.
And there's a mechanistic reason for that. A pill typically targets one specific biological pathway. But when you prioritize deep sleep, for example, your brain activates the glymphatic system.
Which does what exactly?
It physically flushes out amyloid plaques that lead to neurodegeneration while simultaneously repairing metabolic damage across your entire body. You simply cannot out-supplement a lack of sleep or exercise because those behaviors engage the entire system at once.
Wow, that makes a lot of sense. Myth number 3, however, is incredibly encouraging. The myth is that you can age past the point of intervention, but the research clearly shows it is never too late to start. Interventions like rapamycin provided measurable health span benefits in mice, even when administered in the equivalent of their late 70s.
Yeah, the biological hardware retains its capacity to repair itself.
Amazing. Now, the 4th myth is a bit sobering. Despite the flashy headlines, the AI startups, and the billion-dollar valuations, basic, fundamental aging research is severely underfunded at the academic and federal levels. Like, aging research receives less than 1% of funding from the National Institutes of Health.
Yeah, it's pretty staggering.
Wait, less than 1%? With all this hype and the potential to literally reverse disease, how is that even possible?
Because our current medical paradigm is entirely reactive. The funding goes towards studying specific diseases like heart disease or cancer after they've already developed and caused damage. Very little funding goes towards studying the underlying biology of aging that causes those diseases to manifest in the first place.
So what does this all mean? Like, when we look at this $120 billion industry, the question on a lot of people's minds is about the practical application. Is this science just going to become a boutique suite of therapies so billionaires and tech executives can have flawless skin and perfect joints when they're 90? Or does this actually change the landscape of public health?
If we connect this to the bigger picture, the consensus in the scientific community is heavily focused on public health. The goal isn't hyperbeautification. The real goal is compressing morbidity.
Meaning shrinking the time we spend sick.
Exactly. By treating aging as the root cause, you are simultaneously treating Alzheimer's, diabetes, osteoarthritis, and cardiovascular disease. You aren't just extending the lifespan the year someone is alive, you are extending the health span, keeping people robust, independent, and engaged with their communities for decades longer.
That is a future worth aiming for, definitely. So, to wrap up this deep dive, the science is clear. We have cracked the biological code of aging in animal models. We've proven that aging behaves more like a reversible software glitch, a loss of epigenetic information than a permanent hardware failure.
Yep.
But the leap to humans, carefully navigating the dimmer switch of our immune systems and biology, is still in its early, complex stages.
It requires extreme precision to ensure we don't inadvertently trigger harm, like excessive immunosuppression, while attempting to heal the underlying wear and tear.
But the empowering takeaway here is that if you're out on your morning run right now or just listening on your commute, you don't have to wait for the biotech industry to perfect these cellular reprogramming therapies. You already have immense control over your epigenetic software, prioritizing high-quality sleep, regular exercise, mitigating chronic stress, and fostering genuine social connections to combat that systemic inflammation. These are the most scientifically validated methods to keep your biological clock running smoothly today.
Absolutely. There is, however, one final, slightly philosophical question I want to leave everyone with.
Oh, lay it on us.
Let's assume that in the next few decades, scientists successfully clear all these clinical hurdles. Imagine a future where therapies allow your biological hardware to repair itself indefinitely, keeping your cells at the functional age of a 30-year-old. But your brain, your mind will be carrying 150 years of accumulated memories, complex relationships, shifting cultures, and personal experiences. If our bodies stop decaying, how will the human mind handle the sheer weight of living for centuries? What happens to our psychological perception of purpose, urgency, and time itself when the biological clock simply stops ticking?
Man, that is a truly profound thought to end on. Thank you all for joining us on this deep dive into the fascinating frontier of aging. Take care of yourselves and your cells.